Oh, hi.
Hey,
Good to see you.
good to see you too.
So welcome. Let's see. I'm just trying to go through my information over here.
Oh, and John, is your normal format saving the questions till the end or doing them?
Oh yeah, so that's basically, would you, if you would prefer to have questions at the end, then that's great. We could also, if you would like people to ask questions during during the talk, then that's also fine as well. Sort of up to you.
I'm actually fine with either. It doesn't bother me at all to have them during. I feel like it's better than people like not understanding something or wanting to know something and holding it in the whole time. So I'm fine with that. Of course, there's a possibility I won't get through what I plan to get through, but that's like not a big deal. Having a discussion is more important. So I'm happy to take questions throughout. Just make sure you guys like flag me somehow. It's sometimes hard to see. I'll try to pay attention.
Yeah, I know it's always, the Zoom environment is always tricky.
Yeah, if it's a smaller group, like honestly, I'm fine like with people just like interrupting. I'll try to like make some strategic pauses, though that is actually like my weak point. Sometimes I talk fast and there's like no room for interrupting, but people should like just interrupt, or I'll try to watch and see if there's hands up or whatever.
Yeah, and I'll watch for like things in the chat or something like that. I can let you know maybe as we're going along.
Okay. I'm just gonna test something because I figured out this different way of screen sharing where I can like have my notes. Can I just try? I'm just gonna try screen sharing now and just see. Just 1 second. Okay. Do you see like PowerPoint presentation and nothing but a PowerPoint?
It looks like it's maybe just a little bit clipped at the bottom, but
Okay,
otherwise
let me
looks
just
pretty
adjust
good.
it. Does it look like it's getting the whole thing now?
Yeah, that looks perfect.
Okay, amazing, because now I get to see what I want and you guys get to see what you want. Okay, well, now that I just checked that that works, I can pause for a moment. And can you hear me okay? Or is this mic is okay quality? Okay.
Yeah, it sounds fine.
Great. I realized like one thing I didn't think of that it gets so early or gets dark so early here now. And so here it's like nighttime for me. So it's so dark in this normal room. So I had to like try to do some light setup so that you guys wouldn't just see like a dark shadow here.
Yeah, no, it looks fine.
想聽今日個 Colloquium 啊？你 forward 俾我嘅，咁聽啦我哋。你 forward 俾我嘅，咁難得可以由我哋一齊聽 Colloquium。屌我冇食咪。
All right, I guess we'll give like usually give a couple minutes to wait for everyone to kind of filter in before we go ahead and get started.
Fine.
All right, so maybe I can go ahead and start with a little introduction then before we get things going. So yeah, today we're really pleased to welcome Alison Hill, Johns Hopkins University. So she got her degree in physics, an undergraduate degree from Queen's University in Canada, before moving on to get her PhD in biophysics from Harvard, and also the joint Harvard-MIT Health Sciences and Technology program. After graduating, she was awarded a very prestigious NIH Director's Early Independence Award, which allowed her to immediately start her own research group at Harvard Program for Evolutionary Dynamics, where she was one of the John Harvard Distinguished Science Fellows. And as I mentioned, now she's assistant professor in biomedical engineering at Johns Hopkins, where she's also a member of the Institute for Computational Medicine and Infectious Disease Dynamics. And as I'm sure she'll tell you today, her work uses mathematical models to study dynamics of infectious diseases, which has made many important contributions. And it's just a few examples. She studied what kind of treatments might be necessary to cure HIV infection, and also the conditions under which viruses might develop drug resistance. And even beyond real viruses, she's also looked at things like how emotional states can be spread by social networks in a manner that's analogous to infectious diseases. So I'm really excited today to hear about her new work related to COVID-19. Yeah, so with that, let me turn it over to Alison. Thanks very much.
Thanks, John. Thanks for the invitation. And it's really wonderful to see so many people here. I wish that I could meet you all in real life, but this is a good second best for now. Okay, well, just one second. I'm just going to set this up again. Okay. All right, doing my final check. You can see a full slide here, nothing weird getting cut off.
That looks perfect.
Cool. So yeah, I am up for, oops, I don't want you to see that. Taking questions kind of at any time throughout the talk. So if you have a question, please signal to me somehow. I will try to make sure, pay attention, but worst case, just unmute yourself and feel free to interrupt. I will not be offended, and it's great to get the discussion started. So today, just so you kind of know what to expect, I'm going to talk about some of my work on this topic. Normally, like John said, I work most of my time modeling HIV and drug resistance. Of course, with the current pandemic, like many people in the field, I've ended up working a lot on this. But I'm also just going to tell you more generally some of the background to the field of infectious disease modeling. Where does it come from? What are some of the big principles? And then how do we apply those to the particular scenario of COVID? So obviously these days it's hard to go more than an hour without being reminded that we're in the midst of a pandemic, and this tiny virus, less than a micron in size, has really changed life as we knew it. But how can we really understand this? So somewhere in the world, probably not so long ago, this tiny snippet of RNA, which was protected by a protein coat, found itself inside the body of a human. which was a new host that it had never seen before. And just by some crazy chance, this particular virus happened to have some variations in its genetic code, some mutations that allowed it to enter inside the cells of this new host, hijack its replication machinery, and then make thousands of copies of itself. These viral progeny, they found other cells to infect, and they produced even more virus. And this infection took hold in a particular host's body. An immune response was probably triggered, it probably amplified in response to infection, and then set off this cascade of signals to other cells in the body. But somehow, this virus had defenses. It managed to evade these immune attackers, tricking them maybe into a self-destructive pathway instead. And some of these viral particles then managed to hitch a ride on some respiratory droplets that this host might have expelled, like coughing or sneezing, or perhaps just talking. And then somehow, against all odds, one of those expelled viruses not only landed at a second host, but again, escaped its defenses. So then that set off a cascade of infections, maybe first stuttering along on the brink of extinction, and then eventually exploding, taking advantage of these most intimate social networks that humans have created, spreading maybe first within tight-knit groups like families or coworkers, following some travelers heading out of town for the holidays, and then inevitably taking advantage of this global transportation network to spark new clusters of infections in unsuspecting settings. This triggered dramatic and sometimes unexpected changes in human behavior, cutting off many of its transmission pathways, but the infection persisted nonetheless, kind of spreading cryptically in certain subpopulations, hopping around via these residual connections and human contact networks. And if we really want to understand kind of COVID-19 and what has happened here in this situation that we're all living through, and also all the other infections that came before this, we really have to think about all of these different processes. And to me, I think that this story really shows why infectious diseases are really perhaps one of the best real life examples of complex dynamical systems. So just think about the type of questions that have been posed like in the news over the past year really of this pandemic. So questions like, how much do we need to flatten the curve to prevent overflowing our healthcare capacity? Or what would it mean if we try to attain herd immunity? How important are super spreaders in transmitting COVID-19? Why would a therapy that suppresses the immune system be helpful for treating this infection? Are colleges testing students frequently enough to prevent outbreaks? How impactful will a partially effective vaccine be? So these are not questions that can always be answered with careful reasoning alone, and they aren't always things that we can design experiments to answer. So to answer these questions, we really need models. So we need to take what we know kind of about all the interacting parts of this complex system, put them into the formal language of math, and then try to understand the emergent dynamics that come out and how we can perturb those dynamics. So these are the questions that motivate the field of infectious disease modeling, which I work in, and I hope to give you sort of some flavor for this field today. So, oops, there's a spoiler thing that wasn't supposed to pop up. Ignore number 4. So, like physics, the field of infectious disease dynamics is governed by some kind of high-level principles. And also similarly to physics, many of these principles can be understood by considering relatively simple models. So by far the most common class of models are what we call compartmental models. So these classify individuals in a population into kind of discrete stages of infection. And then they track the progression or transition of individuals between these states. So in the simplest, one of the simplest and most common models, individuals can be classified based on whether they're uninfected and susceptible to infection, currently infected or recovered, and then immune to reinfection. Susceptible individuals can become infected only if they contact other individuals who are already infected. So this is a second order nonlinear process, whereas infected individuals can recover at a rate that's independent of their interactions. These dynamics are often represented by a system of differential equations, or we can describe the same process stochastically, just like you would with a chemical reaction. So this model, as I described it, distills a huge amount of variability between individuals that exist in the real world. Like, my disease susceptibility might depend on my general health, or I might be considered more or less infected based on the actual number of viruses in my body at a specific time, but they're still very useful. So one emergent property of this system is that we can summarize many of these dynamics with just one composite parameter, which is called the basic reproduction number, or R naught, which I'm sure you've heard a lot about over this past year if you didn't know about it before. So this quantity describes the average number of secondary infections that one individual produces if they're infected in an otherwise susceptible population. And in this system of equations, it represents a transcritical bifurcation. So when R naught is less than 1, the infection is kind of destined to decrease and die out quickly, while R naught is greater than 1, the epidemic can spread. R naught will be higher if there's more contacts between individuals, if the per contact probability of transmission is higher, or if the duration of infection is longer. So if the recovery rate is lower. And it's really important just to remember that R naught is not really like an intrinsic biological property of a particular microbe. It depends a lot on human behavior and environmental factors. So in a way, it's like maybe an analogy is like the Reynolds number. It depends on sort of this whole situation, not just like one thing, one fluid or one object. So another observation is that early in an outbreak, infections grow exponentially. The system isn't a linear regime. Susceptible individuals are not yet kind of a rate limiting part of this. And this exponential growth rate is not determined by R naught alone, which is important to remember. It also depends on this time scale of infection. And the time scale is determined by the typical time between when someone's infected and when they infect secondary cases. So just for example, like HIV and the common cold have pretty similar R naught values, but HIV outbreaks grow much more slowly because the typical HIV infected individual infects a few others, but over the course of their multi-year disease, whereas common colds are very short-lived. You only have a few days to infect a few people. So the simple model also demonstrates that even in the absence of any interventions, you don't kind of expect everyone in the population to be infected. As the availability of susceptible individuals decrease, the speed of spread is reduced. Eventually it becomes subcritical, disease dies out without infecting everyone. Realized my picture is a little bit of a bad example because I made the simulation with like a pretty high R naught. That's pretty unreasonable, but for more reasonable lower values, it's a smaller portion of the population that will end up being infected. And the time that it takes for the epidemic to run its course, total number of people infected, are functions of R naught, and generally R naught alone. And finally, the model produces the idea of a vaccination threshold or this herd immunity threshold, which you probably also heard about this year. So you can reduce the effective R naught of an infection to be below 1 by moving some individuals into the R compartment by vaccination. And the fraction of individuals that need to be protected this way depends on the intrinsic or sort of starting R naught value. If you introduce a vaccine sort of after some individuals have already been naturally recovered from infection, then this threshold would be lower than what this equation is suggesting. And one thing to note is that kind of in the absence of a vaccine, when infection is just progressing sort of naturally, the final size of an epidemic actually is usually quite a bit larger than this vaccination threshold. So uncontrolled epidemics tend to overshoot this threshold. So this model I'm showing here, it's called the SIR model. It's maybe the most well-known infection model, but it's not the only one. It refers to a very particular type of infection in which someone becomes contagious right after they're infected, and always results in lifelong immunity. And it also ignores, I guess, demographic processes, so like birth and death and migration. So there are many variations in this model that are used to study different types of infection, and we'll discuss them more in the particular context of COVID. So all of these kind of general principles have some pretty specific and important applications to the study of COVID over the past year, and probably heard of many of them being discussed in the news, Twitter, scientific literature. So one of them is this rapid exponential growth. It's observed in many places around the world when COVID first emerged. It's been seen again and again during second and third waves and when control measures were relaxed. And quantifying this exponential growth can be useful in of itself. So for example, for making short-term predictions about the trajectory of cases if there's no more controls applied. And this is still the primary method used in many forecasting applications. And exponential growth rates kind of as high as being equal to doubling times of 3 days, 4 days have been observed. Have actually in many places in the US early in the epidemic and other places. Now in most places, doubling times are quite a bit slower, maybe on the order of weeks. But quantifying exponential growth is not really that helpful for long-time forecasts or kind of building models in and of itself, because we know exponential growth doesn't last forever and it doesn't tell us how strong an intervention needs to be. So for that, we really need to estimate this R0 value. You might think that if we wanted to estimate R0, the easiest way to do it might be just to measure it directly. So maybe observe a chain of infection. And early in an outbreak, you might be able to track everyone who's infected, figure out exactly who was infected by whom, and then actually just count how many secondary infections there were. So this example is actually a transmission network that was started by a group of Zumba fitness instructors in Korea in February. And kind of shows this type of network. But this direct method for estimating R0 can be pretty biased because you're actually more likely to observe these sort of really large transmission clusters where there's some sort of super spreading event, which happened here. You can see there's so many of these red circles. That's sort of the all the people that the Zumba instructors directly infected. So this could bias your estimates of R0 upwards, but also usually if the public health system is aware and tracking a set of infected individuals like these individuals, they're also applying some strong measures to limit transmission. So in this cluster, you can see after a few infections, the outbreak was actually stopped. So this would bias estimates of R0 downwards from what they might be in the general population that's not being studied by the Korean CDC. So for this reason, epidemiologists tend to prefer indirect methods of estimating R0, meaning that we try to back it out from this observed rates of exponential growth using a model or mathematical formula. So remember a few slides ago that this translation depends on the time scale between infections. And so for COVID, this time scale kind of depends on two quantities. The time interval from when someone is infected to when they become contagious, and that's called the latent period, and the duration of time that this contagiousness lasts. So that's often called the infectious period. That determines when a secondary infection could happen and sort of the whole distribution of when those times could happen. So in model form, we're sort of just thinking about this by augmenting this SIR model to include this phase that happens earlier, this E phase, it's traditionally called exposed. So when we estimate R0, we have to actually first estimate the duration of these intervals, which means you have to have some individuals where you kind of have a transmission pair, who infected whom and when, and you can get an idea for these numbers. And then from that, you can kind of use an equation or sort of a model fitting procedure to then get an estimate of R0 value. So for example, I've just shown some calculations here. If you observed different doubling times with these parameters, what R0 would you infer? And this calculation was done a lot, in these references I'm citing here, for example, gave estimates of R0 for COVID of around 2. Now, these estimates have actually been revised upwards. Probably R0, at least the beginning, was actually closer to 3 because of some biases actually in the way these intervals were measured. So if you actually sort of cut off the contagious period in individuals because you isolated them really quickly in your study, you will get a wrong estimate for R naught. So there's lots of interesting things to think about in these calculations. So we talked a lot about the parameters related to infection spread and control, but another really important quantity that infectious disease researchers want to estimate during an outbreak is how deadly it is. So usually what we want to know is what proportion of infected individuals will go on to die as opposed to recover. So here, deaths are in black, recovery is in blue. And this quantity, which is often called the case fatality rate, really what this should be called is case fatality risk, or even better, infection fatality risk is really like the true epidemiological word for this. And estimating this is like a little harder than you might think. It also usually involves like thinking really about what the model is that's going on. So one of the biggest mistakes that people made early in an outbreak was to try to calculate this quantity just by dividing the number of cases at a particular time, like the total cases that have been observed by the total deaths. And models show why this method is very bad and will always give a biased estimate. So I'm just showing a simplified model here, kind of describing this process. And I simulated it, saying that only 1% of people will eventually die. But then when you actually measure this rate, this ratio here during a growing epidemic, that's what I'm plotting in the green curve here, what you would estimate the death rate might be versus what it really is. And this happens because there's a delay that happens, like some time it takes for individuals to die. And so during a growing epidemic, the deaths you're measuring now occurred to individuals who were affected a while ago. That's around 20 days for COVID. And your calculation gets messed up kind of in different ways, depending on how fast the epidemic is growing and whether that growth rate was kind of changing over time. So you need to kind of take that into account in a model when you're estimating it. And so now our estimates of infection fatality risks for COVID will do that, or kind of do different ways where you really wait until an epidemic is sort of over, at least in some setting, and then try to quantify everyone who's been infected using antibody studies, for example. And that also helps with dealing with the fact that sometimes we don't observe all of the cases. So all of these things need to be taken into account to really get accurate measurements here during an outbreak. So with an understanding of these the big picture estimates, sorry, I see a question, which I will pause to answer now. So how can you account for the issue of needing an accurate estimate of the number of infected people? So yeah, I think that's what I said. Usually the most common way of doing that now is to kind of augment reported case data with data from serology studies that really measures kind of some random sample of the population and looks at how prevalent previous infection is in them. So with an understanding of kind of these big picture concepts, and so we have sort of estimates for some of these key parameters, more comprehensive models can be constructed that actually take into account the particular kind of clinical course of an infection, COVID in this case, and that can be then used to make more specific policy evaluations. So for example, one of the main goals of COVID modeling, especially early on, was to understand the potential strain on healthcare capacity due to the portion of infected individuals who end up needing hospitalization or ICU level care. And also, obviously, not everyone recovers from COVID. Some percentage of individuals, maybe somewhere around 0.5 to 1% eventually die. So one of the early goals of COVID modeling was to take into account these later stages of infection, the portion of individuals kind of who progress to them versus end up recovering, and the duration of each stage. So really, this can be represented by adding these extra stages into this sort of SIR style model and then estimating these parameters. These models can also be calibrated to give R naught values and exponential growth rates that are consistent with data that's already been observed at that point. And for COVID, these models, despite all of the uncertainties and the fact that these parameters were kind of being updated at the time, they made it pretty clear early on that if the epidemic was allowed to run its course, we would like massively overflow our healthcare capacity. So that was a pretty consistent finding across all models. I'm just showing an example recreation of kind of some of those models here. So these models also shed important light on the potential impact of kind of social distancing measures. So social distancing, as you know, is any strategies that reduce transmission, like just by sort of bluntly reducing contacts. So attempts to kind of flatten the curve, meaning reducing R naught, but not getting it below 1, do result in lower predicted peaks in these models, including the individuals that require hospitalization. But model predictions suggest that these sort of flattening the curve still doesn't really prevent this healthcare overflow issue. You really need to do like what people started calling kind of crush the curve, meaning actually get R naught less than 1. And that's really the only way to avoid the healthcare capacity issues. So models also gave insight into what we should expect after introducing these type of lockdowns or other really strong interventions. So you expect that as soon as you start an intervention like that, let's pretend it just starts on one day, not like a gradual thing. We expect that the generation of new infections to decrease pretty quickly. So you're really blocking kind of this progression here. However, when you have a model like this, it can actually end up taking much longer, so like weeks, until hospitalizations, deaths end up peaking and turning around. So they can continue to increase for a long time after you put interventions in. And models suggest that and give you an idea for what those time ranges might be. And I think this was something that wasn't totally appreciated and caused a lot of confusion early on. So here I'm just showing kind of for these different kind of measures of infection burden, if we have kind of a perfectly strong intervention versus a pretty weak one, how long it takes to actually kind of see the peak of those different measures. For example, like ICU capacity, it could take a month. And this agrees, I think, really with what we ended up seeing in a lot of data. So here are some epidemic data from a lot of different settings that had early outbreaks that were pretty bad and then introduced really strong measures, at least early on. And blue curves here are kind of case incidence numbers, which, so for example, in New York, you can see those numbers turned around faster after intervention was implemented. But these other metrics about hospitalizations and ICU space and deaths took much longer after the intervention to eventually start decreasing. And that can be explained both by kind of the speed of the epidemic at the time the interventions were introduced and kind of these delays in progression, as well as delays in reporting. So all of these models that I've shown have been adapted to, or can be adapted to these particulars of COVID epidemiology and questions that you want to answer, but they all have one major simplification in the way that they model transmission. And I'm sure you're all thinking in the back of your head many different limitations, but one that's quite important is the way that we've modeled transmission. So transmission occurs when there is contact between an infected individual and a susceptible individual. And so far in these examples, we've modeled it kind of with what's called a mass action process, meaning that the overall rate of infection is just proportional to the total number of susceptible individuals, total number of infected individuals, and some rate constant. And so it's modeled just like a chemical reaction occurring in a well-mixed solution. And if you think actually about all the possible contacts that could occur between individuals and making a network out of that, this assumption is just equivalent to sort of assuming what we call this fully connected network or complete graph. And this might be a valid approximation in certain cases for certain diseases, but in the past 20 or so years, it's become increasingly obvious that this sort of well-mixed population model can't really describe the real world most of the time. Sometimes it's fine, but it can make some results that don't actually give the effects we'd be interested in seeing. So there are some cases when you can really map out the relevant contact network for a disease. So actually during the AIDS epidemic, the importance of sexual contact networks became really appreciated. And this graph actually shows data from a study that asked people about the number of sexual partners that they have. And this is a sort of measure of degree distribution. It's on a log scale. And what it's showing is that there's a huge heterogeneity. Most people have a small number of partners, but some individuals have many partners. This type of sort of long-tailed network, which follows a power law, has a very particular effect on predictions about disease spread. This other figure actually shows a real transmission chain from the original SARS outbreak that happened in Singapore in 2003. And as you can see, most people actually just spread the disease to one or two others. So maybe these people, but then there are certain individuals who spread the infection to an extremely large number of contacts. And this distribution of secondary infections can't be explained by a model in which everyone has the same number of contacts or the same potential transmission. So these are just examples of why human contacts are best described by a more realistic network that encodes which transmission paths are possible if an infection is introduced. Some weird things popping up. Okay, so based on these ideas, it's now common to consider explicit contact networks when modeling disease spread. And these scenarios are usually modeled with stochastic processes instead of differential equations. So, for example, I've just shown a simple version of this equation here, where an individual I can become infected by individual J at some rate beta, only if there's a network edge between them. And usually some type of matrix might be tracking these edges. So the average dynamics of sort of stochastic models and fully connected networks look similar to the differential equation models, showing an example here. But of course, you can get a lot more variability in the outcomes, a lot less predictability about details of the exact timing of the outbreak. And when individuals are structured in this network, their risks of infection might be different. So I'm just showing for this toy example here, as a function of how many contacts someone has, how likely it is that they were infected during this toy outbreak. So individuals have different risks, and that's important to understand. There are also, like many other important principles that have been worked out related to the structure of how the structure of contact networks influences the extent of disease spread. There are just too many references even to include here, and I'm happy to send you some awesome ones if you're interested in this topic. So I'm just going to show kind of a few big ones here. So here I'm showing three possible kind of idealized transmission networks that have different structures. So this blue one is a uniform random network. Everyone's connected to the same number of randomly chosen individuals. This green one, individuals sort of have a position, they're arranged in a ring and kind of more likely connected to other individuals who are close to them with then some random connections. This produces a small world network that's very clustered. There's a lot of interconnectedness. And then this pink one, it's another random network, but individuals have varying number of connections that follow a gamma distribution with a long tail. So there's some hub individuals and then some less connected individuals. So if you just run, say, like a simple SIR model on these networks with the exact same parameters, then if you look at the epidemic curves, you see that the epidemic growth is fastest in this very heterogeneous network. It's kind of boosted by highly connected super spreader type individuals, and it's slower in this small world network where there's a lot of interconnectedness, and that really varies the susceptibility pool that any one individual sees. And also, if you measure the final epidemic size of these networks, so I've showed those as a histogram here, since every time you run it, the epidemic size at the end might be a bit different, then the mean of this distribution is actually like different across these different networks. So it's generally highest in the uniform network and kind of lowest in this heterogeneous network. So this pink distribution is lower. And actually this effect was the subject of a lot of discussion related to COVID over this summer. So the idea was floating around that the herd immunity threshold how many people would need to become immune before the epidemic would start to go extinct, might be a lot lower than the predictions from well-mixed models, because we think there's a lot of super spreading, and that's really important for COVID. And the threshold is lower in heterogeneous networks. Even these simple simulations show it. And that happens because these really highly connected hub individuals are more likely to get infected first and then kind of become immune and sort of block the spread of infection across networks. But contrary to a lot of reports on this topic that were in the press, the threshold really only gets a little lower, sort of for realistic parameters. And if you have a dynamic network, which is really probably how human networks work, it kind of removes a lot of this effect. And there's lots of nice papers showing that. So we became interested in how one very important aspect of transmission network structure impacts COVID spread and control. So think about the main tool that has been used to control COVID around the world. Some sort of social distancing or lockdowns or stay-at-home orders, whatever you want to call them. And to a different degree, these sort of policies reduce the number of potentially infectious contacts, but only outside of households. So none of these policies can do anything to reduce infection within households. And we know that's a really important contributor to COVID transmission. Many of these type of policies actually increase the amount of time you might spend with people in your household. So how does this affect epidemic dynamics? So to get at this question, we created networks that really represented these different types of connections. So household sizes can be extracted easily from census data. You can make a simplifying assumption that all household members are connected to each other. And other types of surveys that have been done over the years allow us to estimate the number of external contacts that people have. It's quite heterogeneous, as you might expect. So then you can really create this sort of two-type network where you have some amount of different sizes of households, which results in some distribution of the number of household contacts and some distribution of number of external contacts that people have in a given day outside of their household. And then this model can be used, this network can be used to kind of simulate a COVID model, the type of model I showed previously, and then implement social distancing measures, which are really just equivalent to kind of removing or downweighting only these external contacts. So one thing we don't precisely know is actually what the relative contribution of these different type of contacts are. So is the per contact transmission rate in a household or outside a household the same, or how different are they? So you might think household contacts were likely to have a higher transmission rate. Maybe you tend to have more physical contact with your household members, but you might also spend more time with a contact outside the house, like someone you go to work or school with. So to look at that, we kind of considered a range of values for the relative contribution of each of these contacts, which can be done by kind of making weighted networks. So we consider external contacts that have the same weight as household contacts, or lower or even higher weights. And found actually a lot of surprising results about how this could affect COVID dynamics. So just firstly, found that when you take into account these realistically structured populations, there's sort of a much higher predicted reduction in external contacts that's needed to stop spread than what you might predict from a simple well-mixed model. And that when you have sort of imperfect social distancing measures, which of course is what we have in the real world, you can get very slow declines in cases. And I think this is really what we've seen in most situations around the world. And of course, if you take into consideration that perhaps spending more time with the household might even increase the amount of transmission that's happening here, that can even sort of further raise this threshold on how good those interventions need to be and how slow that decline in cases might be once you start sort of this social distancing lockdown style intervention. So interestingly, also, the relative importance of these household and external contacts actually matters a lot. So in these graphs, what the y-axis is showing is the final epidemic size. So, at the end, we let an epidemic kind of run free for a little bit, and then you implement sort of some social distancing policy, and then sometime measure the final kind of fraction of the population that's been infected. And based on the relative contribution of these contacts, you can see sort of this U-shaped curve. So what this means is that actually social distancing measures are most effective. So you have least people infected when external contacts either contribute a lot to transmission. So that's sort of up here, because then eliminating them eliminates most transmission, or when they contribute very little, because then even a weak transmission sort of removes the ability for infection to kind of like jump between households. So the worst case scenario is really when both of these type of contacts have relatively similar contributions to transmission. And one thing, and why that really is because then you kind of have enough household spread to keep infection going within households, but also enough spread between households to really allow infection to still have spillovers between them. And that's what makes it really hard to control things by social distancing. We'll skip this. So we also found that this network structure, taking it into account, led to even longer predicted delays between when you started a strong intervention and when the epidemic would actually peak and turn around. So, all those delays with just these slightly different kind of contributions of the different type of connections are shown here. If you have a perfect intervention and when you have still a pretty strong, reducing 80% of contacts out of the household is pretty good, but you can still then get really long times before you see that deaths turn around or before you see your peak in hospitalizations. This can take weeks or even months, and that's just predicted both because you have this delayed clinical progression, but also sort of have this residual spread that happens in households. Households are seeded with infection before you start these interventions, and then that spread can still continue for some time, and it really compromises the ability of kind of social distancing only style interventions to control outbreaks. So far the way that we've kind of been modeling social distancing is just like I was saying, just randomly, removing some portion of these external contacts. But in the real world, obviously, like most things, it's more complicated. External contacts actually are divided into different types. You can sort of think of these as layers of a network. And actually data shows that contacts that you have in a workplace or social contacts are highly clustered, to be expected. So we hypothesize actually that the degree of adoption of social distancing measures is also very clustered, not random. So think about it as like certain occupations are not able to work from home. So like all of those people in that workplace are still working, whereas a whole nother workplace might be closed. Some social groups might pay careful attention to measures, other might not. So when you simulate that scenario and kind of compare it to a more random adoption, at first glance, things don't look so different. Actually, the overall effect and the time until you get a peak and turnaround is not so different. But what we found is that this sort of correlated removal of contacts leads to much longer times to disease elimination. So you can see this tail here. Kind of results in pockets of the network where infection can persist for long times despite interventions, which is bad for control. So it kind of suggests that targeting demographic groups like essential workers where there's pockets of infection might persist with more aggressive measures that might deal with the continual spread despite sort of unable to social distance, just enhanced contact tracing or household isolation could be necessary in some contexts. So these type of models also allow us to kind of take a look and make some predictions about infection risks. So here I'm plotting at the end of an epidemic, the overall risk of infection for an individual in the simulation based on the size of their household. And the model predicts that there's sort of a super linear increase in infection risk with household size. And this is driven by the fact that larger households, there's sort of both an increased risk of sort of seeding an infection from outside into that house, as well as more opportunity for infection to spread within the house. And yeah, this is something like we're sort of testing now with data. And we also used a model to sort of examine this increased risk faced by what we'll call essential workers or other who still had contacts despite sort of social distancing measures, or still had sort of more than average contacts. And sort of under these more extreme social distancing interventions or under weaker ones, there's a relative risk difference. So individuals who were sort of still working outside the house, they had around like 1.5, 1.6 times the infection risk of others in the population, whereas individuals who they weren't leaving the house necessarily, but they had people in their household who had a slightly increased risk, and then individuals who no one in their household was really having sort of above average contacts outside had the lowest risk. So at different times in the epidemic, you might have heard that different regions sort of encouraging these like partial relaxation strategies. So saying that people could potentially form like household bubbles or expanded circles. So you would still minimize your external contacts, but kind of interact closely with another household as if it was your own household. So maybe that's good for childcare or help with effects of social isolation. So we studied this in this type of model. It's a good way to look at this question. And we found that these merging strategies can be safe, but only if a few criteria were met. So we found that they really had to be applied in the context of kind of already steadily decreasing cases and deaths. And if sort of infection levels had stabilized, but were not really declining at the time they were introduced, it usually led to a resurgence of cases if like everyone in the population was doing this. And to avoid this type of situation, actually these merged households could further reduce their external context. So for example, a family that merges decides to share, grocery shopping duties or to share some childcare tasks so that there are less contacts outside the house. And that made these strategies more robust to the stage of the epidemic at which they were introduced. And then this finding actually led us to another sort of surprising and very worrisome problem with the COVID pandemic, which is seems outside the realm of these things, but actually quite connected. So, and it's particularly relevant to the US. So since spring 2020, as you know, unemployment rates have soared in the US, and a huge number of households are very behind on paying rent. Lots of studies have shown this, and are really at imminent risk of being evicted. So it's hard to estimate like the exact number of households at risk. Different studies have tried, if you just sort of look at it being proportional to unemployment, then you might have anywhere from 0.5% to like 5% of all households being sort of imminently at risk of eviction in different US cities, states. Other studies based on surveys and a lot of econ analysis kind of estimate risks of households infection being quite high. And there has been some legislation to try to prevent this. So early on, some cities or counties were making their own kind of patchwork preventions, but they were all about to expire in the fall, which is when we sort of got involved in this problem. And I'll tell you a bit why this is relevant to what I've been talking about with these networks. And so luckily, the CDC actually implemented a national ban on evictions in September for the fall. It's about to expire very soon. And ever since it started, actually, there's been some very high up court challenges to it, really questioning, like, does this actually reduce COVID spread? Or, what do evictions have to do with COVID? So what happens when people get evicted and how is this related? So in general, sort of three different things that could happen. They could find a new house. They could end up becoming homeless and living in a homeless shelter, or an evicted household could sort of move in with friends or family. And it turns out this is the most common thing that happens to evicted individuals. So a huge portion of them actually end up merging households. with another family. So basically in the model, similar to that household fusing bubble situation, except this is sort of an involuntary thing, an evicted household sort of merges with another, and this creates much larger households, which, as you can infer from what I've said before, makes an increased risk for COVID spread in like a very nonlinear way that you really can't understand without models. So we use sort of the same type of models, doing a lot of sort of careful calibration to try to narrow down even more carefully what all these different parameters are, and look at how, based on the sort of predicted number of households that might be at risk of eviction, how much would this actually affect kind of the epidemic in a typical American city, or sort of comparing some different cities. And the results are actually quite staggering. So we found that even with relatively low eviction rates, and we considered sort of the whole range of them, there was substantial increases in sort of the final epidemic size, on the order of, if you have a city of 1 million people, sort of thousands or up to tens of thousands of excess cases that models would predict would occur in the presence of evictions, but not in the absence of evictions. And evictions increased the risk of infection, sort of maybe not surprisingly, for households that were evicted or kind of doubled up with other households that were evicted, but it also increased the risk for all households in the city because of these spillover effects. You have larger households, that amplifies transmission there, and then more chance for spillover. We found that these effects actually were even more exacerbated if you considered kind of disparities that exist in typical American cities. You might think that, oh, our model that's just sort of saying that, it's just a random household that could get evicted, and social distancing is like kind of a random thing. That's not a good example, because it's really just these lower socioeconomic neighborhoods that this is affected by, and this would only affect them. But actually, if you consider models where sort of the same types of neighborhoods have high rates of eviction, but are also the ones where people are kind of less able to socially distance, maybe due to more essential workers, then the effects of evictions are actually more extreme, because that actually leads to sort of more sustained pockets of infection, more spillover, and overall that increases the risk of infection for everyone in the population. So it's really hard kind of to measure this type of thing in studies, but models with kind of our best estimate for all these parameters suggest that preventing evictions, especially during this like massive unemployment crisis, is really important for controlling COVID. This can be applied sort of to much more particular contexts. So, we did this for Philly, where we really mapped out a lot of different details about the sort of demographics of Philly, and that using real mobility data to track measurements and of social distancing, and really the effect is very similar. So I'm gonna finish up there. These effects of population structure have sort of implications for COVID dynamics, even beyond the things that I've talked about. It influences sort of distributions of why you see certain patterns of epidemics in one city versus the other. We were involved in a big study of a huge number of outbreaks in China, and found that we really needed to think about kind of all these levels of organization within a city to understand those patterns. So I just wanted to say that all of this work was done with a really huge team. I'm just the spokesperson for all of this. Some of my graduate students and former lab members did a lot of this work. I mean, graduate students did all the work here, as always. And my collaborator, Mike Levy at UPenn, really led most of these projects with me as well. We work closely with the team at Northeastern on many of these analyses, and we work with some housing policy researchers at Urbana-Champaign that really provided a lot of the insight into how these social factors interact with COVID. And there's some additional reading here. I'm happy to send this to anyone or share whatever slides if anyone's interested. Some of these topics are kind of discussed in this Physics Today article that I contributed to a few months ago. And thanks to our funders who sort of co-opted to support COVID research. And if you're interested in more about COVID modeling, there are a few different sort of forums and conference series. You can learn more about this. I can send you the info for that. So happy to take any questions. And I'm also happy to stick around and just discuss any of these things or, COVID stuff in general, whether it's a question I addressed in my talk or not.
Yeah, so thanks very much for an excellent talk. I am looking for who might be having questions. I think Kirill has a question. Do you want to go ahead, Kirill?
Yes, definitely. But I think there were some questions. Well, one of them was mine, but probably not particularly important in the chat before that. I don't know if you want to start with those.
Oh, sure. I can only see one. Yeah, so someone said, wasn't Ferguson's prediction wildly off the mark? Did they fix their model in the
That was actually me,
yeah.
but there was a
I'm
question
happy to
before
address
that.
Yeah, the question before that, I had, by the time I read it, I had addressed just about like how we try to count all the infected people that we might have missed in cases, and generally the answer to that is antibody studies. Yeah, so your question, so just for people who might not know what this is referring to, is talking about a model put out by a large outbreak modeling team at Imperial College in the UK. Neil Ferguson, who's also an advisor to the UK government, runs that team normally. And so I think this question, and they had made some of the early kind of predictions on how the COVID outbreak might unfold in the UK under different scenarios. And I think, so one, like the absolute most important thing to remember about infectious disease modeling is it's the complete opposite of like weather prediction, for example. So both very complex systems, but there's like one really critical difference, which is that as soon as you make kind of a prediction about what could happen in the outbreak, people are going to react and they're going to change the way they behave and respond, and that affects an outbreak. So like we can't really change the weather. So we can actually test how good our weather prediction models are, or, there's so many other examples in the physical sciences for this, but we can never really, it's very rare for a human infection that we can really compare a model to data. So, I mean, it's impossible to say, like, at some level, we can't really say that model, if we had not have tried to control COVID at all, like, would that many people have died? I mean, it's hard to say because we are controlling COVID. I don't think, I mean, if there's like sort of one particular part of it you're talking about, but overall, I don't think anything in that was like wildly wrong. I think at that time, some of our estimates actually of what % of people require hospitalization or die were a little off. They were a bit high at that point because we weren't sort of aware sort of what proportion of infections were asymptomatic. So we were missing some of them. But I would say that if you think about like how many interventions we're applying now, and I mean, the UK is a great example, and still, I mean, cases are going wild there, and it's not like we're letting it run free, and still this is happening. And when you look at seroprevalence surveys like in the US or the UK, it's not like most people have already had COVID. We're still at situations, in many places in the US where 5, 10, 15% of people in most places are the only ones that have had COVID so far. So like we're a long way away from the end of sort of this natural process.
Anyway, that was like a side question. That wasn't my main question. Ferguson, I have my issues with because I think they just shot their credibility right there when they started talking about the number of people infected rather than how R of T depends on various interventions. Naturally, if you want to be scientifically sound, you talk about R of T. If you want interviews on BBC, you talk about number of people infected. And I think these people actually, in my opinion, they shot their credibility right there, just shooting for cheap publicity. But anyway, be it as it may, my real question is, how self-averaging are your models? So I'm not sure you use the same terminology as we use in physics, but when all of us at some point were armchair epidemiologists, I presume, at least I definitely was. And when you look at various data, it seems like a lot of what we see is fluctuation driven. And that's partly encoded in your models, right? Where you have these super spreader events and whatnot. And then the question arises, if fluctuations are roughly of the size of the signal that you are reading, you might ask yourself, like, what should be the size of the sample where you can actually start believing your predictions? In other words, where the averages that you find tell you anything about what you actually observe. Because if fluctuations keep growing, with the same, with the size of your sample in such a way that the averaging doesn't really tell you the full picture, then you really are not learning much about, so maybe you can make predictions on the size of a country, but even on the size of a city, it's not really particularly predictive. And so do you know how, how quickly the averages start becoming meaningful in your models?
Yeah, I mean, that depends on some details of model parameters in terms of how much sort of variance there is in a model prediction at a particular time. Like in general, I would say for infection models in reasonably sized populations, those fluctuations are not crazy or prohibitive compared to the mean, but that in some sense. So for example, in many of these models, the main thing, a lot of the variance comes in terms of the timing when things might really take off, but once they take off, then things become more predictable. But because of those shifts in time, a prediction at a particular time could have a lot of variance. But this question is extremely dependent on details of population structure that are really hard to estimate and accurately encode in a model. And it's because of this really sort of, let me try to show this hierarchical nature of populations, and that you have most contacts at this very close level, and then more at this next level, and the next level, and you have what in population biology we call a metapopulation model, where at some level things are always going to be stochastic, and while you think by going to higher levels and more people you're getting rid of some variability, that's not necessarily true, because you can have sort of separate populations there that are not in sync, and trying to pool them leads more variability. So this is a very difficult question, and I don't think it's hard to say something general, and it's just very hard to measure this. In general, many of these details of infectious disease dynamics are really not sort of forecastable, I think, in a way you would like them to be. Does someone else want to ask a question themselves? I can read this one that's in here, but it's nicer if you want to come on and ask a question.
Can I just go ahead?
I just put one in chat.
Okay.
Yeah, Barry put one in chat. Yeah.
Yeah, I can read it. Okay, 1 second. So one phenomena you didn't discuss is that COVID and other infectious diseases have waves. So we experience a wave in California, much worse than the earlier one, despite measures in nursing homes, social distancing, blah, blah, blah. How can you describe wave phenomena, magnitude creates mitigating future waves? So again, infectious diseases are not like the ocean. It's not like some natural phenomena causing these waves most of the time. So there are many infections other than COVID that have waves. And honestly, for most of them, we don't really know why. So there are some infections that have waves due to seasonality, some that have waves due to demographic processes, and some that have waves for other much more complex environmental reasons. I think for COVID, most of the waves are due to human behavior, but we do not know why. It's hard to precisely say and explain everything with COVID. Why did this wave happen at this time? This wave happened at this time. Some of it can be explained by a really simple metrics of human behavior. So just measuring mobility and how often people are leaving their house, and you'll see that mobility changes correspond very well to things. But sometimes actually the fall waves that are happening now in most places are actually not really explained by changes in mobility. So we don't know what's driving this, but it's human behavior mostly, probably, and a little bit of environmental, I think, is possible.
But presumed experts like Fauci, for example, was predicting that there was going to be a wave coming in the fall during the summertime. So, I mean, we heard it many, many times. Is that just?
No, I mean, I think it's a reasonable assumption given that like most other respiratory infections.
I would think from your modeling that if we get to a stage where the initial one dropped off, you must know enough about what contributed or how it brought R down if you use R to know how to control it after that. That seems to me it's to predict that there's going to be a wave without any question how you could mitigate it is not
Well,
you
sure. I
don't
mean,
understand it very well.
but I'm saying like we don't know what exactly is driving each of these waves. So it's not clear like why is there a wave going on now? Saying like, you know, how much, I guess the relative role of environmental factors and human behavioral factors like is not clear in a sense that like, you know, we don't have models that can say like, you know, for this temperature and this humidity and, you know, give you some other quantities about the environment, like how infectious is COVID. Like we don't have a model that says that. We don't know that. So that's why it's hard.
So
I know flu has like waves in the winter. Do we know if those are like due to human behavior or due to temperature, or we just know that they happen?
Yeah, I mean, we know that they happen, and we know that sort of both can be contributing, but it's really not like sort of totally narrowed down, like because both of these things are happening at once, right? Like school years and people spending time indoors is like happening at the same time as these environmental things, and some things don't. Like, yes, the flu season like is opposite in Australia, for example, but like it can be relatively synchronized across parts of the US that have quite different weather, for example. So there's not like one explanation necessarily that like gets all of the data.
So can I just ask a question? I know that you're probably not going to have an absolute answer to it, but I just like your comments on it. So obviously the vaccine is coming right now. So there's two things happening. The vaccine is coming and this new strain that's, I don't know, 50% more transmissible, which you must be able to put in your models. And the policy, at least in some states, is to really depend on the vaccine. Now, I know that the vaccine speed is a completely different variable, but you must have actually asked yourselves the question, or some modeler must have asked the question in setting policy as to how these things must beat up against each other and whether or not, you know, Fauci says things are going to be curving over, you know, in April, we're going to be, you know, pretty good. Is that still true given the fact that there's a 1.7 now or R or whatever it is for this new strain, which will probably take over the US in a month?
Yeah. So firstly, like, you know, most things Fauci is saying is like, you know, just very like intuitively based. You know, I don't think Fauci is running or, you know, being given like results from a model that are saying this. So I'm not particularly working on like vaccine strategy models, but there are a few like really good groups who are doing this and like worked out really like sort of optimal vaccine allocation schedules and like, you know, sort of the best way to do this. And of course, like very little of it. So it's only like very loosely being followed. And I haven't sort of seen those models be updated with this strain. I'm sure that they are doing that, and probably it's going to be posted in the archive like within a week or something. So yeah, I mean, it's not something you can do like a back of the envelope calculation, but it's a race. I mean, that's exactly what it is. Like, can we sort of protect enough people before kind of this variant and the spread that it causes really kind of cancels out the effect vaccines. But I don't know the answer to like which scenarios sort of which parameter regimes that's possible under versus which ones it's not.
Okay, I mean, you know, the kind of thing that I wonder about, of course, is the University of California has just announced that it's going to open in the fall. And I would like to know that that might be true. And this seems to be threatening that. So
yeah,
that's the end of my question. I think you're not, I guess,
yeah.
You're not going to be able to answer that, I guess.
No, I mean, it's hard. And just the weird thing about these dynamics is that, like, you know, COVID could be over really quickly if we let it rip through and kill everyone, or if we controlled it really well. But in these in-between regimes, you can have extremely like long-lasting, like sort of petering along, but like still at worrisome levels epidemics. And like it's very likely we could be in that regime, and so that this isn't dealt with by the fall. I hope we're not, but definitely models can give it regimes where that's possible, and they're not rare. So I just saw that Elizabeth had a question. So she wanted to ask about the R part of the SIR model. There are a lot of different estimates for how long immunity lasts, a few months to years, and there's been articles claiming that immune people can still spread the virus through nasal loads. How do people account for this? And how do you figure out how long immunity lasts? Yeah, so there's some really nice papers out there. Actually, I think both of them are published in Science, but they're kind of purely modeling papers looking at how different sort of aspects related to how fast immunity wanes and whether it's sort of full or partial, how that affects like the long-term, like the next few years of COVID. One of those papers, the lead author is, or the sort of senior author is Brian Grenfell from Princeton. And so a lot of interesting scenarios can happen, like interesting as in like, you know, not good for us. So yeah, I mean, there's lots of ways to just, you know, make more advanced versions of these models I've been talking about to include that. Computationally, like I think this is really something that's better measured experimentally. Like you can try to infer this type of thing by like fitting models to data. I mean, there have been diseases and outbreaks for which that makes sense. I think that's really hard to do with COVID right now, and it would be better to have good experimental data. The thing about immune people spreading the virus, still being able to actually like get infected and have high enough viral loads to spread, that's like theoretically possible. I don't think it's very likely, but like I could, you know, there are physiological mechanisms that would allow that to happen. I think my hypothesis is that we will soon learn that immunity and natural or vaccine induced also like really prevents you from getting infection at that type of level. Some people's hands are still up, so feel free to ask a question.
Well, Larry, if you're trying to talk, we couldn't quite hear.
Someone,
No.
I just put another question in the chat box.
Great. So the question is, some countries have controlled COVID pretty well, like South Korea. Luckily, they survived the Zumba dance class outbreak and managed to control things. Is it useful to compare these and others to establish variables in the model? And yeah, absolutely. I mean, people definitely look at these examples and look at what was done and how effective it was to try to understand some things. So I think like, you know, in the Korea example, some things like really effective contact tracing, high uptake of masks early on, outbreak, and even sort of interventions to reduce household transmission. Like there's things like that I think are different that are working and sort of show that when those things are done early enough and sort of with high enough fidelity, they can control things. So yeah, that information is definitely used.
Yeah, I have a question. You extend SIR model to incorporate a different stage. There is the, mild and the hospitalized and the thing and so on. I would suppose the time for each stage or category to be recovered is different, not evenly distributed, right?
Yes.
So then also the transmission intensity also different for each category. I just wondering how you incorporating those information, or actually how you get those information from the real case to run your model.
Yeah, so I didn't really go into all the details of this. I mean, we could give a whole talk on how you estimate all these parameters. Yes, all of those stages have different lengths, and they can have both different average lengths and different sort of distributions of those lengths. And all of that can affect the dynamics. So models can include that, and we try to get that data from cohort studies. So these are studies that follow individuals over the course of their infection, in particular, like ones that end up going in the hospital, end up dying, where we really know like the times at which these things happen and the portion of individuals that they happened to. So that's kind of how we get information on the progression pathways. And then, yeah, another important point you said is like people might be kind of more or less contagious at different stages of infection. And, I kind of showed like a very simplified way of counting for that, just to make it simple for now, in terms of like, there's some time you're not yet infectious and then you're infectious. In reality, based on sort of two things. One, if we actually measure people's viral loads over time, and the more virus you have, the more virus is going to come out when you cough or sneeze, and the more likely you are to spread to someone else. And that like follows this very particular curve shape where it starts very low, all of a sudden it increases super rapidly, and then it starts decaying over time. And we think that kind of contagiousness follows a similar pattern. That kind of relationship can be backed out by looking at these transmission pairs and seeing like what's the whole distribution of how long after someone was infected that they infected other people. And so, yeah, it's not like a constant over time. Some models just simplify it by saying like you're infected in this time period, and not others actually account for the whole trend. And one thing we don't totally know is actually for people who are in these later stages of infection, like if they're hospitalized in the ICU, how infectious they are. It's quite hard to measure. I mean, certainly we know like there is infection that happens in a hospital and lots of healthcare workers have been infected, but we don't actually know kind of how much of that is coming from patients and how infectious someone is like throughout that stage. It's quite hard to measure. So everyone is kind of making some assumptions there. Many people ignore that type of infection completely, and just try to account for infection of people who are not hospitalized. So yeah, it's something that it's constantly being updated in models.
And also for the vaccine, at least to most recent reading I had, they just reduce you, for example, to be less severe. You may still get a mild, or you still carry the virus, or you still can transmit the virus.
We don't know that. So just to be clear, because this is an important point, the trials only tested for the ability of the vaccine to reduce kind of clinically diagnosed infection. It's not that they don't reduce all infections or all transmissibility. It's just that on first pass, they weren't designed to measure that. And it's sort of just about the way clinical trials are designed. So now there's many studies underway now of people who have got vaccinated, particularly at a lot of these big university centers, to measure exactly that, to like make sure that the vaccine is actually preventing you from having virus replicating in your body and spreading to others. And hopefully we'll know the answer to that soon. But it's not that the vaccine doesn't do that, it just wasn't proven in the trial. So like in animal models of vaccines, so for example, like many vaccines were tested in monkeys before humans, and in those cases, the vaccines really did like dramatically reduce the amount of virus, you know, by like 5 orders of magnitude or something in animals. So like, I guess my intuition would be that something similar would happen in humans, but we don't know.
Yeah, we just could learn, you know, from the flu shot, you know, influenza. You know, you got the shot, but doesn't mean you will not get, you know, because also you cannot predict the exact strain that you actually had.
Yeah, the flu shot is a sort of more complicated situation. Someone asked in the question, like, are there any results from our studies that indicate changes in the CDC guidance? I mean, one thing that like, I think that a lot of these studies that look at transmission in households suggest is like, we really need to find better ways to help people not spread infection in households. I don't know like exactly what the CDC guidance are saying about this, but I think a lot of people have a misunderstanding about this, like just from what I've heard, that people think that, you know, it's basically guaranteed that you're going to infect everyone in your household. What can you possibly do about it? But it's not true. Like in general, people, you know, do only infect some fraction of people in their households. And studies have shown that, you know, with sort of better infection control measures that, you know, you can do in your own household, like you can reduce that. So like this is something people have control over, and dealing with this like would definitely help in the US.
All right, so I guess if there are no more you know, immediate questions, let me thank Alison again for a really great talk and lots of interesting discussion. Yeah, so I guess this is the time when our you know, normal colloquium will end, and then if you still have a little bit of time, I know there's some graduate students who would like to meet afterwards, if that's okay.
Yeah.
Yeah, and I guess we can probably just stay on the same Zoom meeting if that's all right. And maybe if you want to take like a quick break, or
I might just like summon my partner to bring me food, but I will stay here. Yeah, thanks everyone. Really good questions. I always love talking to physics audiences because I feel like, and I just, you know, sort of forgot about this when I was in physics, like, you know, physicists don't really take anything for granted and really like push all the assumptions of everything to the limits. And I think that's really an important thing to do. And obviously in this type of talk, I can only kind of cover so much of this, but if you ever, you know, want to chat more about all the details of things that go into it and these type of models and what people are thinking about or not thinking about and how you make it better, like I'm always happy to talk about that.
Yeah, that sounds excellent. Yeah, thanks so much. All right, so I will, let's see.